can exotic objects such as neutron stars or black holes swallow dark matter? What will happen to them if they keep doing it? How can this help us to figure out the nature of the enigmatic dark matter? Find the answers to these questions in today's episode of my weekly astronomy news podcast, Astro Edge. Are you ready? Engage!
Welcome to Astro Edge, weekly broadcast presenting highlights of leading-edge research in astronomy and astrophysics.
Today I'll be covering two recent papers which have a common topic. One of them is neutrino signals from neutron star implosions to black holes. The first author is Yossef Zenati. He is a postdoctoral fellow at Johns Hopkins University in Baltimore, Maryland, United States. The second paper is a dark matter probe in accreting Pulsar-Black hole binaries. The first author is Akil. He is from the Hong Kong University of Science and Technology Institute for Advanced Study. These both papers talk about an exotic object such as neutron star or a black hole exposed to dark matter. Both neutron stars and black holes, and specifically stellar mass black holes, are a result of an explosion of a very massive star, so-called supernova explosion. As you can see from this table, for very massive stars, at least 9 times the mass of our own Sun, such stars live short lives, and at the end of their lives, they explode as supernovae. During the explosion, they shine as billions of stars. Theoretical models tell us what happens to the star after it explodes. Depending on its original mass, and also depending on some other factors, it can either become a neutron star, a black hole, so-called stellar mass black hole, or in some cases it may leave nothing behind. Now about dark matter. Dark matter, this is the stuff which scientists believe makes up most of the matter in the universe. 5-6 times more than regular matter like atoms, gas, planets, stars, etc. Something we can see. As the name suggests, dark matter is the kind of matter which we cannot see. And the only way we can detect its presence is on how it interacts gravitationally with visible matter. So the original evidence for dark matter came from analyzing how galaxies spin. Scientists applied the standard Newtonian law of gravity to galaxies, and they discovered that they spin much faster than it would be the case if they only had the visible matter. It looked like there is much more of invisible matter inside galaxies. Even though this was the original proof of existence of invisible dark matter, it's important to remember today there are many other totally unrelated proofs of existence of dark matter. So the concept of dark matter is very solidly established, even though we haven't discovered it yet. For example, galaxies tend to cluster. So there are large groups of galaxies, we call them galaxy clusters, and inside those clusters galaxies move like bees in a swarm, and they move according to the gravity they exert on each other. And again, the same problem. The speeds of galaxies moving through the cluster of galaxies is much higher than it can be explained if you just account for regular visible matter. There must be some invisible dark matter in much larger quantities. But that's not all. Gravitational lensing is another proof there is dark matter. When we observe remote objects, remote galaxies, and there is something in front of it, a cluster of galaxies, sometimes we see distorted images of the background object. This is so-called gravitational lensing. This is predicted by Einstein's theory of relativity. And again, the strength of this lensing can only be explained if we add much more dark matter into this foreground cluster of galaxies than what we can actually see. Another independent proof of existence of dark matter is the cosmic microwave background. Microwave background is the radiation we can see coming from all directions in the sky. We need special microwave radio telescopes to see it. This radiation is believed to be a snapshot of the early universe when it was only 400,000 years after the Big Bang. We see tiny fluctuations or ripples on the maps of cosmic microwave background. And the theory which tries to explain these ripples requires a presence of large amounts of invisible dark matter. Yet another proof of existence of dark matter is the structure formation. Those tiny ripples in the cosmic microwave backgrounds with time grew and became galaxies and clusters of galaxies. Again, if there was no invisible dark matter, there was just not enough time for those tiny ripples to collapse and make galaxies we see today. There must have been significantly more dark matter than visible matter to make it happen, to make galaxies happen. So what's the connection between dark matter, something enigmatic we still couldn't detect in our labs, couldn't really figure out what it is, and exotic objects such as neutron stars and black holes? I remember many years ago I gave a talk at one of the amateur astronomy clubs, something about dark matter. And someone in the audience asked me, what about you have a black hole and there is dark matter? Would it absorb dark matter? Would it suck it in? And I didn't have the answer. I thought, yeah, sure, it probably should be the case. But at that time, I don't know, 15, 20 years ago, there was no such research, nothing I was aware of. It was something fairly obvious, but scientists didn't really think about that at that time. Now the time has come. Now it's an active area of research. If you take an exotic object, super dense, like black hole or neutron star, and place it in a galaxy, that's where we actually normally find these objects. What naturally should happen, these exotic, super dense objects should start accreting or gobbling up dark matter surrounding them. And that can lead to very interesting and even unexpected results. This first paper is talking about a neutron star. Neutron star is an object with a mass, maybe 2 solar masses, which has a size of maybe 10 kilometers. It's extremely high density object. Such objects are expected to suck in dark matter. As time goes on, that will lead to increase of its mass. And what this paper discusses, at some point, the neutron star becomes so massive that it can no longer be a neutron star. It is a well-known effect. Once something is too large to be a neutron star, it should become a black hole. This paper describes how it can happen. It's talking about implosion, and that there would be a disk of ejecta material surrounding the former neutron star, and eventually that object would turn into a black hole. Such an implosion would produce a burst of radiation, burst of neutrinos. These are the particles which are very weakly interacting with regular matter. We have special neutrino telescopes typically sitting deep underground or deep under the ocean surface, which try to detect these particles coming from the sun or coming from astrophysical objects. And also, there is an expectation of gravitational wave signal. Gravitational waves are ripples in the space-time itself, as predicted by Einstein's theory of relativity. These waves result on objects moving slightly closer to each other and then slightly further away by an extremely small amount. You need extraordinarily sensitive telescopes, gravitational wave telescopes, to detect these ripples in space and time. But scientists do have such telescopes now. The conclusion of this paper is that this effect is possible. Indeed, neutron star should at some point swallow enough of dark matter to turn into a black hole following an implosion. And the paper also tells us how this implosion will look like. It will have very unique signature of a neutrino signal, gravitational wave signal, and regular radiation signal. We haven't discovered such objects yet. This is a theoretical paper. It gives us a blueprint. If we ever discover something unusual, a burst of radiation, maybe accompanied by neutrino signal and maybe gravitational wave signal, if what we see is matched to what this theory predicts, that maybe we discovered the very first transformation of a neutron star to a black hole from absorbing dark matter. The second paper also talks about neutron stars, black holes, and dark matter, but in a quite different context. What it's saying is that we still don't know what dark matter is, and the paper suggests there is a way to try to discover dark matter nature. All we have to do is to discover what is called Holy Grail of black hole astrophysics. A binary object, a pulsar, a neutron star which acts as a pulsar, which radiates energy on a very regular basis, orbiting a black hole. Such objects haven't been discovered yet. But the theory predicts there should be at least a few dozens in our own Milky Way galaxy and many more in other galaxies. So it should be possible to discover them. And with the upcoming radio telescopes, it should be possible. Once we discover these very exotic objects, they can tell us a great deal about a lot of things, about general relativity, for example, but also, as this paper suggests, perhaps they can help us to understand what is the nature of dark matter. So how it's going to work? It happens that when you have a binary object, a pulsar, a neutron star orbiting a black hole, we can use radio telescopes to measure the orbital motion of a neutron star around black hole with extremely high accuracy, just unbelievably high. That is thanks to the extremely high regular impulses coming from the pulsar. So when black hole gradually absorbs or sucks in more and more and more dark matter, it becomes heavier, and that is actually something we can detect. This paper tells us once we discover such objects and observe them for at least 10 years or so, for certain types of dark matter, we should be able to see that effect. So the essence of this paper, this gobbling up of dark matter by a black hole, the rate of absorption of dark matter depends on the kind of dark matter. So currently the most popular candidates for dark matter particles are WIMPs, which are weakly interacting massive particles. A very different kind of particle is an ultralight dark matter, and yet another very different possibility that dark matter is actually a collection of very small so-called primordial black holes. This paper discusses one by one these different candidates, and it shows that the rate of growth of mass of black hole by absorbing these different kinds of dark matter depends on its nature. So by discovering hopefully multiple objects of this kind, binary pulsar black hole objects, and by observing them for 10 years or longer, we will be able to see how much, if any, black hole mass changes with time, and that in turn will let us figure out what kind of dark matter is contributing. According to this paper, WIMP kind of particles should be detectable with this approach. Same applies to ultralight dark matter. But in case if all dark matter consists of primordial black holes, the paper suggests this method will show no change in black hole, simply because the growth would go not in the continuous absorption of dark matter, but rather quite infrequent absorptions of primordial black holes. So infrequent that we would not be able to see such an effect in our lifetime. In conclusion, the two kinds of exotic stuff which we know exist. One is the exotic objects, compact objects such as neutron stars and black holes on one side, and enigmatic dark matter on the other side. What is becoming now a mainstream research is that exotic objects should be absorbing dark matter. And that should be something which can result in interesting effects, something we can discover, like implosions of neutron star, which becomes a black hole after absorbing too much of dark matter. Or if we discover the holy grail of black hole astrophysics, the binary black hole pulsar object, which we can measure with such high precision that the tiny effect of black hole absorbing dark matter should be measurable with the upcoming future technology in the next 10 years or so. These are exciting times. Research like this is extremely important to help us think ahead and plan ahead our future missions, future radio telescopes, and be prepared for the discoveries which are for sure coming. In my book, these two research papers do have an edge. I'd really love this stuff to be seen as many people as possible. because of the YouTube algorithm, it's very important for you to give me a like, subscribe to my channel, and leave a comment under the video to make this happen. Thank you very much and see you next time.